Okay, welcome all. We have 8 panelists today. We have Ivan, we have Evan, we have Alex, we have Chris, we have Yannick, we have James, and myself. And today we planned for about 3 problems. They are all quite challenging. And if we have time, we can maybe talk about the 4th one. If we don't have time, then we can just go wherever we are. But I think we should be able to complete these 3 questions. The first question is what? Is continuation to talk about that John Conway's paper, The Power of Mathematics, that I showed you guys last time. And this time we are going to share one of his proofs for a very tricky geometry question. It's called Morley's theorem. And the theorem is very interesting. You start with any triangle, and you draw, instead of angle bisectors, you draw angle trisectors. And then they form equilateral triangles, right? So, Ivan, you want to share us the screen for that problem? On me to share it. I can share it.
Yeah, you can go.
Right?
I have it here, okay. But
yeah, you can share it too. Okay. So, well, actually, those lines intersect with more points, so they form more equilateral triangles. We just find the 3 easiest one to see, right? So now we start with any triangle ABC. We draw at every point we draw trisectors, right?
Mm-hmm. So these angles are congruent.
Yeah. So this problem it's quite hard to prove, right? It's many proofs involving some kind of computation, right? If you Google it on the Wikipedia, the one they showed you is a computational approach. I have seen this proof from a Russian book called Plane Geometry. It's in the 1980s, and now AMS have the book translated in English. It's written by Prosorov, and it's in his book too, about proving of the theorem. The proof is also a little bit more synthetic, okay? But no, regardless, all the proofs we have seen is quite difficult, okay? And John Conway, in his lecture, he gave a very nice proof using good logic, basically, right? What his approach is, he starts with this middle triangle, the equilateral triangle, and he said, I can recover the original triangle, regardless of what angle you give me. Say A is 3x, B is 3y, and C is 3z, right? He said, I can just construct this triangle now. So in that way, he proved it, because ABC to construct this PQR is clearly uniquely determined. So if he can recover ABC, that has to be the triangle he wants to prove. So what's his idea? His idea is, for example, he said, I started with PQR, I can construct ARQ, for example. Mm-hmm. Right? If I can stack ARQ out, by the same reason, I should be able to stack BRP out and CPQ out. And by that time, I already have triangle ABC. And if they satisfy all the angle conditions, then I'm done, right? So the key is to figure out what is this triangle ARQ. ARQ, we know, one of the angle we know is the X that they give us, right? And we don't know anything about this R and the Q for now. If we know one of them, of course, we know the other one. And they are equally difficult because all the conditions are symmetrical, right? So we give our audience 5 to 10 seconds to think about how do they find out this ARQ. Because in Conway's article, he basically already claimed what is R and Q. So this actually reminded me about one thing. When you guys later on gradually, when you start to read the academic papers, you have to take a very critical eye in learning it. I mean, critical is not about being, it's very constructive. You try to learn, but you also try to digest everything to make sure everything is yours, rather than you are still just following. Because if that's the case, then 2 months later you will never remember what you learned. This is one tragic thing I see young students when they preparing for math Olympiad. They try to remember solutions. So, for example, they study Evans' wonderful book and learning geometry, and then after 2 months they forget all of them because it's not theirs, right? They only read his solution, right? If you can do all the exercise on your own, maybe only do half of them is enough, right? But it's not like by reading and memorizing. And this is same. If you read his paper, you will find it very magical. How come suddenly he knows those two angles? And you have to ask yourself, how do I know those two angles, right? Well, the key is this. This is how I see it. You see lots of angle trisectors. Trisectors means what? They cut angle in 3 times. That's very difficult. We like angle bisectors, right? Because then we can use angle bisector theorems or those things. Incenters relate to angle bisectors. So I look at a Q, for example, right now. I can see it's almost incenter because it's the intersection of 2 angle bisectors of which triangle? It's A and C and something extension that Ivan is drawing. Because that's clearly the incenter. Because I have 2 angle bisectors and they meet at Q. So our students who are listening here, they clearly know, oh, the angle bisectors intersect, right? So let's call this point, say, B1, right? So Q is the angle bisector of B1. And in angle bisector, if you draw another triangle, just draw a random triangle on the side. If you draw another triangle, and just draw 2 angle bisectors from the base angle, we should be able to figure out that center angle, right?
So if this is x, z, z,
yeah,
this one,
yeah,
180 minus x minus z,
right. And we know both x and z right now, so we know if we connect B1 and Q, we should know, right?
We should know that these 2 angles,
right?
Or and you want that?
Right, we want that angle, right? So what can we about this one are Q and P? They look like what? They look like a kite right now if you draw very well, right? Because I know RQ is equal to QP. And I also know they share the common side B1Q. And oh, it's the incenter, so no, I know at B they split.
Okay, those 2 angles are same, right? So it's like SSA?
It's like SSA, yes. You said this in a very good way, not the other way around, right? Yeah, SSA is good, right? SSA don't give us congruence, but SSA almost give us congruence, right? In what situation SSA is not congruent? Is actually these 2 angles R and P, they might add up to what? 180 degrees. Otherwise, they should be congruent to this 2 angles, right? So what I mean is, we know this. We know most of the time RQB should equal to PQB. RQB1 and PQB1. Most of the time. These 2 triangles should be congruent. Right? And we know that's what? Isosceles triangle, right? Equilateral triangle, right? So we know each of them is what? 30 degrees. And that basically helps us to figure out what this angle, the question mark angle now. Because we know AQB1, so it's what, like you said, it's 180 minus what? X and this. Also, it's basically X plus this Z and something, right? So more or less now we know what is AQB1 now, if we know that's 30 degrees.
Okay, so if I redraw it here, right, we have two diagrams. I think I understand what would be half of this angle. This is how I am. Half of this angle, exactly this half, is going to be 90 minus x minus z, right?
Yes.
And this angle is 30 degrees. So I can find the question mark.
Yes.
It's going to be 30 plus 90 minus x minus z.
Yes.
Which is 120 minus x minus z.
Right.
Which I can also rewrite as 60 plus y, because x plus y plus z is 60, right?
Right? So that's how we know the question mark is 60 plus y. And by the same token, we know the other angle should be 60 plus y, something, right? By symmetry. It should be 60 plus z, right? Because y goes with z here, and this angle and the q should be 60 plus z. So that's how we know the angle of this what? Of this AR.
60 plus z.
Yeah.
60 plus 4.
Yeah. So now it's good. So by the same, we should figure out all BRPs, PQs, right? And that's how we know we can construct this triangle now, right? But our audience are still maybe confused. We are using a very important thing here. We are saying PQB1 and RQB1 are really congruent, right? And they are congruent is because side-side angle. And we know side-side angle usually is not congruent for two triangles, right? We are assuming what? We are asking ourselves only in what situation actually these two triangles are what? Are not congruent, right? If they are not congruent, it's only when this angle R and angle P here, they add up to what? 180 instead of they are equal.
But is it possible? Let's think. If it's true, then what should be true? I think then our quadrilateral should be cyclic, right? But is it possible to be cyclic? Let's think about it. PQR B1 is cyclic, right? Well, let's check. Well, I know another pair of angles. One is 60, so angle at B1 must be
120.
120.
Right. But that's possible, right?
If
right? That's very possible because if x and y, x and z satisfy certain ratio. For example, x and z add up to what degree? Add up to 30, you are okay.
Right, so pretty much angle y must be equal to
90 degree.
90 degree?
Right?
Y must be 30.
Y 30.
Yeah, y must be 30, right? Yeah, so angle B is 90. Right? So here comes the important logic part. In this triangle, I can always start with an angle that is not 90, right?
Okay, that would work.
Right?
Oh God!
All three angles 90, right? I only have one 90. I can always avoid that. So I can always start with an angle that assuming that this B is not 90, and then I can have exactly the same argument to make sure all these angles are true. But when two of them are true, the third one is forced because all these angles you know. For example, you know what's AQC because that has to be 180 minus x minus z. So all those angles are done and force out of the last angles too. Right? So I think that's his logic. Now you know all the angles are what? Are fixed. And then you can start to build, right? So if you push the paper up, because I don't want to take too much time on these questions because I think our audience can still figure out more of them on their own. So now what happened is I know the angles of these three small triangles that's sticking out.
So x.
No, we do not know. We know the three small ones is in the middle.
Okay, x.
Right, we know that one.
Y and 60 plus z over here.
Yes, right? We know those three sticking out, right? So now we want to make sure is how do we define those two pieces over here so they can match perfectly and they match together. So over here, you guys still have to do something a little bit more careful thinking. You could think about this way. On this obtuse triangle, you start with Q, you know the middle angle because you know X and Y, right? And you can say angle Q here is 180 minus X and Z. That you know. And you also want to make sure AQ and AO here, they match. So you can basically define this angle by side, angle, side. But that's not the best thing to do because angle, side, angle, side angle side does give you this unique triangle. But the issue is you do not know how do you know that's X and Z, right? So I think it's much better if you flip this triangle to the other side to make sure this angle X is defined here first. And then you also flip what? This little angle at C and to flip to that side and to define this triangle this way instead of angle, side, angle. Then you can define this all together and then put all these 7 triangles together. And then your job is done, right? So what we have is we have to cover lots of detail. But his idea is extremely wonderful, right? It's basically saying, okay, I basically know these angles, I construct, I'm okay. And that's the best part of those geometrists because they know the rest of it is for the algebra people to do. They tell you how to construct, right? And you are done.
So wait, let me explain the difficulty because I'm trying to follow and I think I understood why it's difficult. So we start with this 60, 60, 60, right?
Uh-huh.
And we said that we can construct this X, this is 60 plus Y, and this is 60 plus Z, right?
Yeah.
And then we construct this one in the same way. We know all the angles and we know all the angles here.
Yeah.
The trouble is, if you connect these points, you still don't know if it's X and Z, right?
Right. So the whole problem is completely to Conway's approach is basically a logic puzzle. So he didn't do it this way by saying that triangle had those X and Y angles. Instead, he flipped this one X outside again to build this triangle, right? He defined this fat triangle separately. Yeah, he makes this flip.
So he makes this flip and he gets this angle X.
Yes, and then he made the other flip and they're on the same line Y, and then he want to play, basically that's a line.
Okay, so this is Z.
Because all the angles are known.
Yeah.
So wait, what is this angle, guys? Maybe you help me.
This has to be 60 plus what? Plus A, right? Because it's computing 60 plus X. Yeah.
Okay, so this is 60 plus X.
Yeah.
So pretty much we want to show that these points are on the same line.
With that, yes.
Sorry, they are definitely, well, I made them not to be, so we don't.
Right. So it's go back to the original one, you might see it better that way, to draw those 2 lines.
Okay. So those this
that
way.
and that. Yes. And there are 2 beta plus 60 plus C angles. Both of those 2 angles are 60 plus C, 60 plus Z.
Okay, 60 plus Y over here, right? Because we reflect.
Yes, and that's the triangle. Okay, so we leave a little bit more detail for our students to finish, and then let's just stop here, and then we can move on, right? So this gives you an idea about this very hard theorem.
Zooming, someone asked you, why is Morley's theorem important?
Oh, actually, I do not think it's a very important theorem, at least for Math Olympiad, because you hardly use it, right? It's a unique structure. But actually, when I was a graduate student, I heard this from my advisor. Somehow, this thing defines an elliptic curve because it's the intersection of some cubic things. So people can analyze more about this in higher mathematics. But I do not know. Yeah. But I think there is an article about that. How do they connect to, higher mathematics, right? But as for Olympiad, I think this is one of the theorems is almost it's nice, but almost it's useless. It's basically this is about it, right? It's not really very applicable to other things.
I really like this idea with 90 degrees, and I think our audience can learn from this, because sometimes in the competition you have a good idea, but you need to patch it up a little bit, make some sort of tweaks to make it work. And it's a cool skill to have.
Adding on to what Yvonne says, I think a lot of the value for this problem in terms of Olympia is just kind of like just adapting the kind of ideas you see in this problem. There were two like really tricky ideas. One is kind of like a, well, it's not really a phantom point idea, but the kind of general idea of like changing your perspective, changing the fixed values, and then solving a different problem like reverse, and then just like proving uniqueness.
Yeah.
I think like for an example, I think like this is one of our solutions on our Olympia IMO team in 2018 for the problem 6. Involves something similar to this. And this is a technique that's been viewed many times. So if you're ever stuck, it's always like a good idea to see, oh, what if I change this other fact and see if I can prove this way. Another good idea is like the 90-degree argument. You can probably use something like continuity there to kind of like deal with the bad cases, and just like kind of like being able to logic through like the edge cases and what you can do to fix them using continuity in cases is pretty good too.
Well, that only works if you first draw a good diagram to show that those 4 points actually aren't cyclic, right? You have to first realize like what you're trying to prove.
Next question, we move on.
Yeah, so you guys can read the question here, and I can put a poll, and let's see if our audience guesses what is the origin of this problem.
Most and panelists can't vote.
Why can't I vote anymore? Wait, where's Taiwan?
It's
Which one of us is going to propose to China?
Zooming, right?
Yeah, oh, really?
Zooming totally proposed to China.
Oh, interesting. Okay.
Michael Ren can.
Oh, no, not the official Chinese.
Oh yeah.
Never mind.
Almost everyone voted 80%, so I'll close the vote and I'll share the results. China won, Canada and UK second place. Very good.
Someone asked why is Russia not an option?
Yeah. If I see the problem Russia is an option, I would definitely vote for Russia.
Looks like a Russian graph theory problem.
Yeah.
Okay, let's read it. Yannick, maybe you can read it for us.
Okay, so
this is from what? Alex just wrote this for 2020 Canadian Math Olympiad, right?
yeah.
Wait, when did the Canadian Math Olympiad happen?
It was in early March. I mean, I wrote this problem a long time ago, but we ran the test in early March.
Why doesn't the USML happen in March? Wouldn't that be better?
Well, who knows?
Might happen next March.
Okay, so there are 1 to 20 people on a social media platform where any pair of them may or may not be friends. I guess here friendships are mutual. And for any group of 60 people, there are at least 60 pairs of them that are friends. How many friends, that is pairs of people that are friends, must there be in total among the 120 people?
Is this the minimum?
Yeah.
Are we looking for minimum, right?
Yeah.
Yeah, I take that to be implied.
Yeah.
What's the smallest number of friendships that have to exist?
Yeah.
Yeah, so I guess we're talking about this problem. I can share my screen. Well, once Yvonne enables me to share my screen.
Done. Sorry.
I'm good now.
This problem is hard.
Starting to unmute myself. Sorry. Yeah. So basically, for this problem, it's like, well, for every 60 people, you have like 60 friendships, right? And then, well, you have another group of 60 people here, and then you have 60, and then you have another 60 friendships, right? So the answer is clearly 120, right?
Well, this one time is way too fragile. Like if you just cut it a different way, if
Yeah,
you just cut through some friendships, you could just.
Yeah, so I guess the first point of this problem is you want to find like what the answer is around, right? Like you want to figure out if the answer is like linear in 60 or it's like quadratic in 60. So why should it be linear or quadratic?
Well, I mean, I think the condition seems to suggest the density of the edges should be closer to linear. Like, if you're ostensibly in the actual equality case, when you pick 60 people, the number of edges won't be like way more than 60. So you expect the average degree to be like O of 1.
Yeah, I mean, I think that's like pretty good intuition. It's like, well, like if you assume that like you have like, oh, you basically try to satisfy this inequality greedily, right? Like for any group of 60 people, there's like so many inequalities. You just try to satisfy them. You expect to not lose too much, like on the worst group of 60 people. So, well, it's linear. What other bounds can you get? Well, one standard thing you can try to do is something like, I'm going to do some text. So every group of 60 people have 60 friendships out of 60 choose 2. So you can still see my screen, right? Mm-hmm. So number of friendships is at least 60 choose 2 over, 120 choose 2 over 60 times, times 60 over 60 choose 2, right? Because it's basically saying 60 people randomly, they have 60 friendships. So that means that if you choose if you sum over like all choices of 60 people, then you have, sorry,
This seems
something wrong. But,
yeah, this seems large. Actually, no, this doesn't.
but this is like around 4 times 60, right?
Yeah.
It's like you can get a lower bound of like linear that's pretty close. So, but the problem is still like you need to figure out what the answer is. And the other line of thought is, well, what if you just try to consider a configuration and try to prove some bound without knowing what the answer is? Well, one thing you can always do is, well, I guess there's like 2 things you can do, and I'll just suggest one of them just because the other one doesn't work. So one thing you can do is you consider basically a set of 120 people where there's a minimal number of friendships. And this seems to not work because it's hard to like control the number of friendships well. And the other thing is you just consider a group of 120 people that satisfy the conditions. And then in those, you consider a group of 60 that has the minimal number of friendships. So I'm going to erase this thing here. And I'm going to say this red 60 here.
Alex, can we look for maybe a symmetric graph in some sense with the same degree per person that would fit the description?
Yeah, I mean, if you want to try to guess, yeah, sure. So if you have a symmetric graph.
My idea is because you have the same number of friends as people, we should choose a bunch of triangles in our equality case. So like if we're choosing like our 60, we want like 20 triangles or something as our like worst case.
Yeah.
I guess. Because otherwise, if we have shapes that are bigger than triangles, then ostensibly, like, those will be tied together with other things that are bigger than triangles. Yeah. And then they're together will be bigger than, like, hexagons.
Yeah, so basically it's like, one thing you can do is you can consider, well, it's not hexagons, but you consider, like, splitting these 120 people.
Complete hexagons.
Yeah. Maybe, like, the worst case is, like, you split these people in half, right? You just, like, split these people in half. That was not very happy, but so like say there's 3 on the top and 3 on the bottom, right? And if each clique of 6 people has like everyone's friends with each other, and if you split it in half like this, then the top half will have like basically 20 triangles, and the bottom half will also have 20 triangles. which gives you 60 friendships on the top and the bottom. Yeah, so this is the equality case. So, I mean, first of all...
Wait, Alex, and if you don't cut it in half, then what? You have 2 and 4, which is better?
Yeah, it's convexity.
Well,
Okay.
you see, if you do 2 and 3, there's like 6 friendships in total, right, among these 6 people after you do the cut. If there's 2 and 4 now, there's 7, but you still have to do some averaging argument to show that like the top and the bottom both have at least 60 friends. Right? But since we mentioned the equality case, what's the answer here? So answer equals, what is this? This is 15 times 20 equals 300, right? Because there's, in each group of 6, there's 15 friendships, and there are 20 groups. So there's just 300 total. So if we have 300, let's try to aim at 300 now. So I think one thing we want to do is try something where we make something minimal, and I'll just tell you the thing that you want to make minimal is consider 60 people with minimal number of friendships between the 60. So this is the 60 red people. So what conditions do we get once we know about this? Well, let's have a person outside, right? So the simplest thing to do is, what happens if you make your group of 60 with the person outside? Let me draw a red dot. What happens if you replace this red by this blue? So this means that number of red friendships is less than or equal to number of blue friendships, right? Where the number of red friendships, I'm just saying, is the number of friendships among these 60 people, and with blue friendships, with this one extra person, right? But basically here, like, you see the difference between the red and blue charts is basically just the number of friendships this one person has, right? This one person maybe has like a few friendships here, and this red person maybe has maybe not the same friendships, right? So what does this inequality mean? Well, it actually means that, so number of friends of red person is the most number of friends of blue person, right?
Among those 58?
Among the red group, I guess.
Yes, among other
59.
59 red.
Okay.
So now what? Well, the problem is, like, here you're saying, like, for every red person, every blue person. So this is true no matter which blue person we choose, right? But this inequality is a bit awkward if you try to change the red person, because if the red person changes, then these other 59 red people also change, right? I guess the next step is to write an inequality that's true for every pair of red and blue people that doesn't make reference to which red person it is. So I'll try to write it here. And for every pair of red, blue people, number of friends of red person among red people, let x equal this.
This is any arbitrary red person, right?
Yes, yes. And among number of friends of blue person. Because we want to have a general inequality just because we want to combine these inequalities together. So what do we have? What's the relation between x and y?
So x is at most y. Is that what we have?
X is at most y. And if red, blue people are friends, then if the blue person is also a friend with the red person, then you don't count that friendship, right? So that means x is at most y minus 1.
Cool.
And okay, so from the perspective of someone who has not solved this problem, this is good so far because it matches our equality case, right?
No. Well, if you guess that, sure, if you guess that this is the right answer, then sure, it's like because every blue person is friends with 3 red people, and every red person's friends with two red people. I mean, it doesn't completely match, right? Because if you have a blue person that's in another group of 6 people, then
Oh, I see.
it doesn't completely match.
Okay, yes.
And then you cover over. You also now to introduce a group of 60 blue people.
Well, I guess you don't need to introduce a group of 60 people, right? Because like this inequality just here, x is less than or equal to y. This is already really strong. So this means that because in particular, max of x is less than or equal to minimum of y, right?
Mm-hmm.
Max over all red people. All red people, red and blue pairs. So what if the max of x is 3? Well, if the max of x is 3, then the min of y is already 3, right? So what does the max of x being 3 mean? It means that there's a red person with 3 red friends. If that's true, then the min of y is at least 3, which means that every blue person has 3 red friends, right?
Oh, and that gives you already 300.
Exactly. That already gives you 300
That's
because
60
yeah,
plus 60 plus 180 plus 60.
Can you actually draw out the equality case with the red and blue a little more explicitly? I think probably a lot of people can't follow it. Just
yeah. Sorry, I guess I only said it via text. Yeah. So that was not red.
Yeah, like I think if you draw the triangles, it'll be easier to follow by a lot.
And blue. The equality cases where you have these groups of 6 that are all fully connected. And then you get the minimum for the bound by just cutting through here. Where basically like all of these edges are connected. Like all of these are friendships here. So I'm just use another color just because it's not part of the splitting.
So in this case, we have x equals 2 and y equals 3 for everything, right?
Mm-hmm. So in this case, we have x equals 2 and y equals 3 for everything.
Right.
But
the problem here is that even when they're not friends, we still have this.
Yeah, the problem is you need to, because the problem now is like, well, first of all, if you say that x is 3 for some red person, right, then you're already done because, you can, no, it's select. Red. Not the right way to can, but so if x equals some red person, then every blue person, total number of is at least 60 red people, 50 blue people, plus 180 blue plus red people, right? Because we know the blue people also have at least 60 friends. And the 180, it comes from the fact that every blue person has 3 friends. So there's a total of 180 friendships, 3 times 60 for every 3 for every blue person. So if every red person has at most 2 friends,
And it's a loop or what?
It has to be exactly 2 friends,
Yeah.
or not
Yeah,
exactly. It has to be.
No, I think it does have
2.
to be exactly 2 because you need average degree at least.
Yeah.
You have,
Yeah.
So you just have a bunch of loops.
you do need exactly 2, right? Because then number of red friendships equals, or at most 2 times 60 over 2 equals 60 by double counting, right? Mm-hmm. If you can imagine, like for every red friendship, you count it by each of the people in the friendship, and then you have most or at least 120 like per people with red friends, but every person has at most 2, so it has to be equality. So what does that mean then? So that means that among the red people, basically, well, every person has exactly 2 friends, right?
and now you know basically what it looks like because it's a bunch of cycles. I see.
Yeah. So I mean, you can even draw out the red stuff. Yeah, exactly. You can draw. I mean, you don't know how large the cycles are, but
Sure.
Sure, we have some cycles. And then what if you're a blue person now? So now the other condition you want to use is if the red and blue people are friends, then x is less than or equal to y minus 1, right? Mm-hmm. So if you have a blue person here, well, how many friends does this blue person need to have?
Well,
because this blue person is friends with at least one red person, right? Can you assume that or not?
So
don't we have
at least 2 friends already?
So we basically know that each blue person has exactly. It's the only way they have more than 2 friends if they're friends with an entire cycle triangle, right?
Wait, what?
Is that correct?
I mean, you're already in a pretty restricted case, right? I think one way to argue is basically just like, okay, so now this blue person has, you see, x is at least 2, right? X is equal to 2. So every blue person has at least 2 blue friends, right? Yeah. Or 2 red friends.
Oh, sorry. Yeah.
Let's just say this blue person has this red friend already, right?
Yeah. So now because the point is now they're all equal, so the 2 becomes a 3.
Yeah. So now the blue person actually has 3 red friends as well. And then we can do this counting thing again because every blue person has 3 friends. So
wow.
I guess my assessment of like what was hard about this problem is like, I guess you guys like quickly found the answer, right? Like if you don't know what you're targeting, then it's very hard to come up with this argument of like saying assuming some red person has 3 friends. Like this argument here, to get rid of this case, like seems hard to come up with because you don't really know where you're bounding, right? You don't really realize that you can just throw out this case. I guess this is the problem where, well, I guess the context is basically, well, I was like doing my math homework like sometime while I was in school, and then I was bored, so I decided to like come up with a problem, and then I came up with this problem. It seemed like it was not trivial. I spent like 2 hours trying to solve it.
When was this?
This was I proposed the problem in like 2019 before the CMO, because I proposed it at 2019 CMO. But it wasn't accepted, and it was accepted in 2020 instead. So yeah, I felt like basically I realized I solved the problem. I found the answer, and then it was like much easier to solve the problem somehow. Because there's still a lot of other pitfalls you can like. There's a lot of other things you can try that don't work so simply, and we're just showing the simplest solution.
Do you know how many people solve it at the real contest?
I don't know, but I'm guessing around 0, just because it was a common test, which implicitly means that fewer people try it, right?
Okay. How are there like alternate solutions that are pretty good? This seems like
there was a solution on E08 that was pretty good. I haven't understood it fully yet. It seemed to solve a much harder problem.
I think on a similar line, if you try to maximize the cut instead of just minimizing the.
Let's stay on this page just in case.
Max cut. Yeah, I think you'll get a similar result.
I think there's this post on E08 where they prove something more general, which doesn't use the fact that like I'm using half the edges or something. But I haven't read through this argument completely yet. So there are definitely alternate solutions. I guess we try to find some. I mean, like with this type of problem, like there's a lot of ways to attack it because you see like the equality is like pretty weak in some sense.
I think that just the jump from 2 to 3 is very tricky.
Right, because somehow like 2 is like everything just like works, and then 3 is like, well, it's kind of like the point is you have this statement here where you want to get an inequality for all red blue pairs, right? Like you want this very awkward statement here, where instead of considering one particular pair of red person and blue person, consider all such pairs and have some global inequality there.
I mean, I think once you come up with the minimality argument at the beginning, I think that this falls out pretty easily. Like this is pretty immediate. So I don't think the generality is the hard part. I think jumping this considering the minimal extremal argument at the beginning, and then just like the actual like jumping from 2 to 3 is like.
I mean, sure, there's obviously like a lot of things you can try to minimize, right? Like the first thing I tried to minimize was basically like to just try to consider some the social media platform where like the number of friendships is minimal or something, and then try to put some bounds on that.
Yeah.
Alright.
Yeah, I mean, I think for me, when I was trying this problem, I actually tried this problem on like video a couple days ago, and it was a disaster. Didn't get anywhere. But I just didn't have the idea at all to look at the 60 people with the minimum number of friendships. I was trying to do something with a Tehran type argument where it was yesterday. Okay, never mind. I'm losing track of time. Apparently, it was yesterday. But I was like trying to look at a maximal independence set or something like that, and try to like grab 6 independent sets to do a Tehran-like argument, and it just like doesn't work. Incidentally, I'm curious, like, what happens if you mess around with the numbers? Because the reason I was pushing the Tehran so hard was because if you replace one of the 60s with 1, it's basically some version of Tehran's theorem, where it's like amongst some sort of vertices you have at least 1 edge, and so this is a problem where among some sort of vertices you have at least 60 edges.
I think the same argument goes through with like 60 replaced by maybe 30, 90, 120. I think all of these will work.
Yeah, it seems like
I mean, assuming you can do the equality case.
Yeah. I mean, ignoring the divisibility. Like, the actual Tehran has, like, integer division issues, too. But,
I think it's a different type of integer division.
Wait, the equality case is also just very different, right? From Tehran?
No, this is an equality case of, like, Tehran with... This is the graph
This
with
is the
the
opposite.
fewest edges
Yeah.
such... The complement of Tehran. This is a graph with the fewest edges such that among any 21 vertices, there's at least 1 edge.
Yeah.
That'll be interesting.
Yeah. But some of this solution is really using the fact that you're cutting it exactly in half. Well, it seems like you should do something even if it's not exactly in half. But
Okay. How about let's stop and here and we can move on to the third question.
Okay.
Yeah. This is quite hard. I still have to try to understand the whole thing. Yeah. Let's go on to the third one now.
That's what they do nowadays. They just take any graph theory problem and they throw it at the last problem of the test.
Well, combinatorial problems tend to be hard. I agree.
I don't think when's the last time there was a graph theory problem that was not number 3? Oh, there's a China TST problem. The one with the terrible equality case.
okay, so let's see if I can get this to work.
Alex, you need to stop sharing.
Yeah, well, my setup takes a little while to set up, so. Okay. Okay, and then I want to.
Alex, someone was asking what the social media platform was for that problem.
I think the original statement doesn't even involve.
Yeah, they originally just actually said the word graph, right?
Yeah, it was literally just a graph theory.
Is that even legal? I thought you weren't allowed to do that.
Well, there has been like RMMs with graph theory
I'm just
problems.
kidding. I'm kidding.
Yeah, it depends on who you ask. Different people have different opinions on that. Alright. Cool. So, I guess this problem will go by pretty quickly, so I think I can fit it in the time I have left.
You can see, right? Okay, yeah.
Okay. So, in this problem, I have a quadrilateral. So, right, so let's do, well, I'll initially draw it like this because this is how you typically draw a quadrilateral, and I'll probably redraw it later with a different orientation. So A, B, C, D. 13.
We don't see it yet.
Oh, sorry, let me figure out this. Okay, there we go. Oh, jeez. There's going to be some other stuff showing up. It's fine. Okay, so I have a quadrilateral ABCD, and this guy's 13, and the other one's 20, and then I'm given that ABC has area equal to some random number. This is 338. The area, the other one is 212, and the problem asks for the minimum area of minimal possible perimeter, but because I mean, you're given 2 of the side lanes already, so really it's just asking for
AB plus CD.
yeah, min AB plus CD.
Diagram seems to be not to scale.
Yeah. Well, we'll redraw it in a moment. So I think this is a problem that's actually mostly about drawing the diagram in the right way and like thinking about which things are able to move in the right way. So sort of the first thing, this quadrilateral has like a bunch of degrees of freedom and they're kind of not talking to each other in a nice way. But what can I do with these areas? Well, because I have this, they share a common base. So if I take this extension of the line CD, what this is actually talking about is I have some heights that are fixed. And so rather than looking at areas, I'm going to kind of drop them right away and say these guys are fixed. And now you can see this diagram is like really off the scale because one of them is the relative sizes are not correct. So we'll fix that momentarily. But this is equal to something fixed, and this is equal to something fixed. And if you do it this way, well, which things in the problem can I hold still and which things can I move around? So, well, what you can imagine is because these guys are fixed, which one of these is also moving?
So BC can move around, right?
Yeah, so BC can move around in here. The AD, I think, can't actually move around because what you can do to visualize it is this thing, whatever this difference is, and I'm really going to pick. Okay, let me just fix the labels now. They really should go the other way. So let's do. So B and C can move around. But this guy here is the difference between two fixed numbers. So it's also not going to move around at all. And this guy here, as a result, is also going to be equal to some fixed thing because you have a right triangle. This one is fixed by subtract. And this guy is fixed by the Pythagorean theorem. So rather than viewing this problem with reference to the quadrilateral ABC, I have this grid-like thing that's basically held in place. And I'm going to kind of use this instead. So I'm now going to redraw the entire problem with using this fixed grid guy. So let's do A. There's a point A, and there's a point D. And I'm not going to compute the numbers yet, but actually I might not compute the numbers at all, honestly. This whole rectangle and this little length up here are all kind of held in place. And what's moving is just this B and C, which are kind of moving around down here on this line 13. This is, well, that line doesn't matter. I'm not even going to draw it actually. And then I have, I want to minimize this guy plus this guy. So sort of when I like just rotate the diagram and like anchor certain things in place, it's suddenly like much easier to think about. It's like the whole green thing is not moving, and I have this little line BC that's moving, and I can kind of either slide it left or slide it right, and I want to minimize the sum of those two red lengths.
Yeah.
And it looks very familiar from Phillips Exeter material.
Oh, was this a Phillips Exeter?
I mean, I have a general idea.
Everyone in the entire school is required to spend 2 years solving this.
I see. Yeah, because what's happening is this 13. I mean, this 13 doesn't really do anything, right? What I can do is I can imagine you slide this thing all the way to the left, right?
Right. That becomes very direct reflection.
Yeah, and then this becomes a problem that I think almost all of you have probably seen before at some point, where I have 2 points, and you'll hear this problem go under a lot of names. I think the one that I first heard of it is like you have like it's like a river or something.
Yeah.
This is A, this is D. These are in place, and you want to minimize the diff. You want to run to this line and up. And I mean, you've probably seen how you do this. The idea is you take the reflection D prime here, and then you take the one such that these guys are in a straight line. And so that's sort of that's sort of how you solve the problem. Is just you try to figure out which things you can hold in place and then which things you can move around. And it also kind of shows you how I wrote the problem. I kind of wrote the problem in the other way, where I was like, okay, I have this river problem. Well, what if I change the river problem slightly by adding this little gap in between here, this horizontal gap. But if you write it this way, it still looks really silly. And so what you can do is you can be like, well, how else can I turn this problem around so that it looks at, it's the same idea, but how can I at least make it cosmetically look different? And the way you can do it is you kind of change the things that are allowed to move and phrase the whole thing in terms of just that quadrilateral ABCD. And then in that case, all you're fixing is the heights.
Yeah, you disguised the old problem quite well, right? Because
it doesn't look like it at all.
Yeah.
Yeah.
When I first thought about it, sorry, I was not fixing A and D. I fixed B and C, and my AD was a segment that was moving along two parallel lines. And it was very silly. I was like, something difficult.
Yeah. Also, 212 is not divisible by 13.
I was very sad.
Yeah, I'm sad.
I looked this up. Was this number 25 or something?
It was kind of late. Yeah, it's actually, when you look at it the right way, it's trivial. And if you look at it in any other reference frame, you can't tell what's going on.
But doesn't everyone just compute coordinates on OMA?
Maybe.
I think it's 2013. 2013 people are still decent.
I see.
No, but you still have to choose the right axes, right? You have to choose BC as the x-axis or y-axis or something. So if you choose the wrong axis, coordinates are harder.
I think people can figure out the height thing, right? So.
Yeah, but as soon as they start to figure out the height, they start to nail down this shape, because that right trapezoid give you lots of things.
Yeah, that right trapezoid.
That's true. Yeah. Very cool. This is how you change an old problem to a new problem, is it? So should we stop at here? We're about 2 minutes off, so that's very good, right?
Sure.
Good, very good. So I think every audience could still go back to think about Alex's problem a lot, right? Yeah, it's still very hard, okay? Yeah, maybe we can revisit that someday. Good, everyone? Good night?
Good night. Good night.
Good night.
Someone asked me what my background was.
Yeah, I want to ask you the same question. What is that thing?
Never mind that.
I mean, it's a green screen, but I cannot tell who's the person in the background. At
the beginning, I thought the last time you used it, I thought you were in some office. Then I realized that guy was never even moving.
I am in some office.
Just not the office on
screen.
Some would say I'm in the office.
What? Okay.
Is that the name of a show or something?
Oh yeah. Oh god. I feel like that show has become a meme because of the lockdown, but I don't remember. I have no idea why. I think
you guys are disappointed.
Okay.
By the way, guys, if you want to see behind the scenes video, I posted it. It's very cool. 3 videos. 3-minute video. 3-minute video. So.
Okay.
The last one was cool because they developed a nice problem out of it. Okay. I'm leaving. See you guys. Good night.
Have a good night.